Authors Xing-Dong and Pourang Irani. The topic of the talk is WristWhirl, one-handed continuous smartwatch input using wrist gestures.
Thanks for the intro. Sorry. So, hi everyone. My name is Gong, and I'm a PhD student at Dartmouth College. Today, I just want to talk about a project called WristWhirl, one-handed continuous smartwatch input using the wrist gestures. So this work was in collaboration with Pourang Irani and my advisor, Xing-Dong. So before I get into the motivation and the related work, first of all, I just want to show you what is the WristWhirl and what WristWhirl can do for our users. So this is the WristWhirl. With WristWhirl, user can pan a map using the same hand wearing the watch. User can also draw a triangle to open a calendar app or play a game like Fu Ninja. So, WristWhirl is a new input style for the smartwatches. Users can use their wrist as a joystick to perform two-dimensional continuous input, including common touchscreen gestures, like drawing a triangle or a circle. Users can perform these gestures using the same wrist wearing the watch. And performing these wrist gestures can minimize the screen's movement. So, two-dimensional continuous input, one-handed input, and a stable screen. These are three most important features for the WristWhirl. So I will talk more details about implementation and applications later in the talk. But before that, let's get back to motivation and the related work. So interacting with current smartwatches often necessitates both hands for scrolling and gesturing. But in many situations, two-handed interaction with smartwatches will interrupt our current context. As you can see in this image, the user has to stop his bike in order to interact with his watch. It is quite inconvenient for our users. So let me just show you another example. So this user is carrying some very heavy bags. It is very difficult and troublesome for him to track the incoming message. Yeah, the bags is so heavy, so the user is shaking his hand, and believe me, he's not getting Parkinson. So there are also some similar situations, like when you are grabbing a handle or a bus, holding an umbrella in a raining day, or holding your child's hand. So one-handed interaction with smartwatches can provide another way for you to free one hand. So we are not the first one who considered one-handed interaction with the smartwatches. This table shows four categories. The horizontal axis shows discrete gesture versus continuous gesture. And the vertical axis shows unstable screen versus stable screen. So for shaking the watch, this is the only technique that has already been applied in the current smartwatches. However, shaking the screen is discrete and may blur the watch content. For the finger pinch and hand posture, yes, they can keep the stable screen. But they only support discrete gestures, which leads to limited interaction. In the previous talk, Robert just showed us a very cool technique that can detect hand posture. But in their work, they only focus on the discrete gestures. So for tilting the screen, it is also very difficult for our users to keep the screen stable. As you can see in this video, when users is tilting his screen, his body also needs to move in order to keep track of the watch content. So WristWhirl fills in this gap. Our technique can support two-dimensional continuous gestures without significantly affect the screen stability. As I mentioned before, WristWhirl uses wrist as a joystick to perform two-dimensional continuous gestures. Actually, wrist is one of the most flexible joints in our human body. Wide ranges of motion makes us to think, why can't I just use wrist as a new input modality for the smartwatches? So before we spend a lot of time and effort into implementing such a technique, the first thing we want to know is that whether it is possible, feasible, and accurate enough for our human beings to use wrist to perform common touchscreen gestures. This is the reason why we need to conduct our first study. In order to reduce the bias, we built a commercial motion tracking system in our lab. And we use 5 Wacom infrared cameras to capture the real 3D coordinates of our wrist and record the trace of each gesture. We use the laptop for showing the instructions to our participants. There is also a treadmill because we are also interested in whether our users can perform these wrist gestures while they are walking. So we asked 15 participants to come to the lab and ask them to perform these 8 common touchscreen gestures. The upper 4 are the directional marks, very common for navigating large workspaces. And the lower 4 are the free-form pass gestures, much more complicated gestures, including triangle, rectangle, circle, and question mark. We picked these 8 gestures for diversity because straight line, curve, corner are all included, and they are quite common in the touchscreen gestures. So we asked our participants to perform these gestures in 4 different conditions. Hand down when standing, and hand up when standing, hand up when walking, and hand down when walking. So here are the results. For test completion time, the y-axis shows the mean time, and the x-axis shows different gesture type. The blue bar shows the down hand position, and the orange bar shows the up hand position. From the chart, you can see that it is quite efficient to perform these wrist gestures. And for the directional marks, it takes about 500 milliseconds to perform 1 gesture on average. And for the free-form pass gestures, it takes about 1.5 seconds to complete 1 gesture. Even it takes the longest time to perform a rectangle, and it still can be completed in 2 seconds. So we also evaluate the screen's movement by using the mean translation distance. The y-axis shows the mean distance, and the x-axis also shows the different gesture types. The blue bar this time shows the standing state, and the orange bar shows the walking state. So when our users are walking, the mean translation distance is about 24 millimeters. And when our users are standing, the translation distance is only 9 millimeters. So in order to help you to get a better understanding of these 2 numbers, I put a 1 cent coin here. So the diameter of 1 cent coin is just 90 millimeters. And 24 millimeters is just a little bit longer than this coin. And 9 millimeters is just half of the coin. So we can see that while performing these wrist gestures, the screen can keep stable. We also evaluate the accuracy of these gestures. For the free-form pass gestures, we use $1 gesture recognizer to recognize the gestures. And the result of 12-fold cross validation reveals an accuracy of 93.8%. And for directional mark gestures, we use a different method because we are interested in how straight were these marks drawn and how close were the marks to the desired direction. For the straightness, we can receive 5.4 standard regression error. And for the angle error, we can receive 9.4 degrees. In order to help you to get a better understanding of these 2 numbers, I put 2 extreme cases here. The left one is a very precise one, with a standard error of 0.4 and the angle error of 1.67. The right one is a very imprecise one, with a standard error of 21.3 and the angle error of 11.6 degrees. So from those numbers, we can find out that it may be a little bit difficult for our users to draw some lines in some specific degrees, but they can draw these lines straight. So, based on these positive results, we decided to build a prototype to demonstrate the feasibility of the WristWhirl concept. So this is our prototype. We built our prototype with 2-inch TFT display and a watch strap augmented with 12 infrared proximity sensors. Each of those is composed of 1 emitter and 1 detector. It operates at 940 nanometers, which distinguishes its signal from the visible light. We also attach a piezo sensor inside the watch strap. It can detect the sound of pinch gesture propagating through the human skin, so that we can use the pinch gesture to indicate the start or the end of the gesture. This is how our prototype works. We treated data from each proximity sensor as a vector, the direction of which is determined by the sensor's location, and the length of the vector is determined by the sensor's value. So here, I put 12 corresponding vectors in the middle of this page. When you bend your hands upwards, the sensors on the top will get a higher value. And this grayscale ring shape also shows the sensor's value. The gradient color is interpreted by the sensor's value on both sides. The higher the value, the darker it will be. So we pick top 3 vectors to merge and to normalize so that we can control the absolute position of the cursor, which is represented by this blue circle. And you may notice that the hand on the button is not wearing the WristWhirl because I just put it there for demonstration. We also evaluate the performance of our prototype, but due to the time limit, we decided not to present them. If you feel interested about it, please refer to our paper. So next, I'm just going to show you a user is using the WristWhirl to perform common touchscreen gestures. User can draw an L, draw a triangle, draw a question mark, draw a rectangle, and draw a circle. So next, I'm just going to show you some applications. So we built 4 applications to demonstrate the possibility of the WristWhirl. The first application is a gesture shortcut app. User can draw a triangle to open a calendar app, or draw an L to quick dial a number to a friend called Lisa. The second app is a music player app. A long wrist swipe can help users to skip a list of songs, and a short wrist swipe can advance the one song at a time. The third application is a 2-dimensional navigation app. User can pan a map using the same hand wearing the watch. User can also rotate their wrist to zoom in and zoom out. So the first application is for the game input. User can tilt his wrist to control the Tetrimino in this Tetris game. Also, user can play full ninja using his wrist. Of course, you need a little bit training to play like this. So far, I have introduced all the interaction techniques of the WristWhirl. Next, I'm just going to discuss the limitation of our work. So for learnability, users still need to learn to perform these touchscreen gestures precisely by using their wrists. And for the implementation, because we are using infrared proximity sensors, these sensors could be interfered with the infrared noises in the environment, like the remote control of our TV. And there are also some daily activities like knocking on a door or knocking on a table could cause some more false positives of the pinch detection. And last but not least, WristWhirl does not support multi-touch gestures. So WristWhirl opens a big space for many new possibilities. As we all know, it is very hard to do the test input in the current smartwatches because the screen is so small. So we are thinking about using the WristWhirl to do the test input for the current smartwatches so that the user do not need to use the other hand to tap on the small screen. We also envision this technique can be used by the blind people because they always need to hold a guide stick or a guide door. Blind people can use the WristWhirl to control their smartwatches or send some very important messages out. So to wrap it up, performing wrist gestures can be quite efficient, and the user can draw common touchscreen gestures precisely. Watch screen can keep stable while performing these wrist gestures. So with that, I'm more than happy to take any questions. Thank you.
questions? Yes.
Hello, I'm Ray from Taiwan University, and it's very interesting work. And I have a question about when you're in your user study, and do you ask the participant to keep the palm like flat, or they can just do the finger pose, or again maybe in the crunch as they want? Because I'm not sure the finger movement will interfere your detection, or.
I'm not sure. So we ask them to perform this. The same 8 common touchscreen gestures. We just give them the instructions of doing this. So we are not.
I mean, in your video, the hand gesture is always like this, palm to keep in flat, right?
Yeah, using the wrist, rotate their wrist, or tilt it.
If their finger do some other movement, will it interfere your detection?
Okay. Probably not, but. For the most of videos, I just put it. Let me think.
Or do you ask your participants?
No, actually, you can do gestures like this. But because the proximity sensor will not detect that distance, it will detect just near the watch band.
Okay, thank you.
Other questions? Yes.
For your talk. I have a quick question about the optimization. Have you ever tried to optimize the number of the IR sensor, the proximity sensor? I think too many IR sensors have been used for your work in comparison with the number of gesture possible. So could you tell me more?
Yes. So here I use 12 infrared proximity sensors because you can see the sensors is a little bit big. So it can only include 12 infrared proximity sensors. But if the technique advanced, maybe I can use some smaller sensors. So here I just build a prototype, and we think from the study we can find out that the 12 proximity sensors is enough for detect at least most of the common touchscreen gestures. Yeah.
I was also curious about. Oh, it's here. Hi. Thank you for the talk.
Yeah.
Have you tried different type of mappings? So, for example, I realized you draw on the vertical axis by doing this movement.
Yeah.
Rather than, for example, this movement that would be mapping with your screen, right? If you actually are facing to the face watch and I want to go on the y-axis, this might be more intuitive, perhaps, than not doing this movement. So I was wondering, have you tried different kind of mappings or different ways?
So right now, no. So maybe we can leave it for future work. So we use the same mapping in the different hand posture when they are doing different hand posture. Yeah.
We have time for one more question. I have a question. Does it matter whether the user wears the wrist on their dominant or non-dominant hand in terms of their ability to accurately perform the gestures or ergonomic?
Yeah, probably yes. But so in our user study, we ask them to use their non-dominant hand. So we want to get a real result of, because users always wear their watch on their non-dominant hand. So we don't ask them to use to draw these gestures in the dominant hand. Maybe with the dominant hand, users can draw these gestures much better. Yeah.
Thank you. Let's thank the speaker one more time.
Yeah, thank you.